June 1816, upstate New York. Farmers step outside expecting early summer growth, corn pushing through soil, oats taking hold, fields turning green. Instead, they find frost. Not a light dusting, a hard freeze that blackens leaves and stiffens the ground like early winter. Within days, snow begins to fall. Not in the mountains, not in January. Snow in June, settling over land that should be feeding entire communities. Livestock hesitate at the edge of frozen pasture that should be fresh and green. Families begin rationing early, not because of panic, but because they can already calculate what this means. No crop now means no food later. And this isn't a single event. It happens again. Another cold snap, then another. A growing season that never stabilizes, cut into fragments before it can even begin to function. Vermont reports the same thing. New Hampshire logs frost in July. Massachusetts records ice forming overnight in shallow water. Move across the Atlantic and the pattern expands. France reports relentless cold and rain. Switzerland documents failed harvests and early shortages. In Germany, crops don't ripen. They rot in fields that never dry. Britain records one of the worst agricultural seasons in decades. These regions don't share the same geography, the same weather systems, or even the same planting schedules, but they share the same outcome: fields that don't produce. And when multiple independent systems fail in parallel, the question stops being what went wrong here and becomes what is happening everywhere. Because this doesn't look like a bad season. It looks like something overriding normal patterns at scale and doing it fast enough that no one can adapt in time.
The official explanation is clear and widely accepted. April 1815. Mount Tambora erupts in Indonesia with a force that ranks among the most powerful volcanic events in recorded history. Ash columns rise over 40 kilometers into the atmosphere. Sulfur-rich particles spread across the globe. Sunlight is partially blocked. Temperatures drop. A volcanic winter. Ice core data supports it. Climate reconstructions align with it. On paper, it works. But when you compare that model to what people actually experienced on the ground, the fit becomes less precise. The average global cooling is estimated at less than 1 degree Celsius. That's enough to disrupt climate patterns, but what we see in 1816 goes beyond a mild shift downward. We see repeated hard frosts in the middle of the growing season. We see cycles of brief warmth followed by sudden collapse. We see rain that doesn't come as isolated storms, but as persistent saturation that prevents any agricultural recovery. These are not steady conditions, they are unstable ones, and instability is far more destructive than a consistent decline. Crops can adjust to a colder average. They cannot adjust to repeated interruptions that reset growth again and again. Look at the timing. Tambora erupts in April 1815. The worst agricultural disruption peaks in mid to late 1816. That lag makes sense, but the way the disruption unfolds does not follow a smooth curve. It spikes, it fluctuates, it hits in waves. That matters because agriculture depends on sequence, on predictable transitions between planting, growth, and harvest. Remove that sequence and the system doesn't just produce less, it fails to produce at all.
Before 1816, the system appears stable on the surface. Harvest cycles repeat with variation, but within limits. One region underperforms, another compensates. Markets adjust. Transport moves surplus to deficit areas. That's the baseline assumption, a system that is fragile but functional. Then 1816 arrives, and that assumption begins to break. Because the moment crops fail, the pressure doesn't stay in the fields, it moves through the entire structure. Grain failure immediately affects feed. Feed affects livestock. Livestock affects transport. Horses and oxen are not optional. They are the engines of distribution. When they weaken or die, movement slows. And when movement slows, even regions with partial harvests cannot support others. The system starts losing its ability to balance itself. Prices react quickly. Grain costs rise sharply, not gradually. That's a signal. It means those closest to production are already seeing failure before full data is available. Bread becomes expensive, then scarce, then inaccessible in certain areas. People begin substituting whatever they can find: lower quality grain, roots, anything that can stretch supply. This is not inconvenience. This is structural pressure building in real time. Because early 19th century agriculture is local, immediate, and dependent on timing. One disrupted season doesn't just reduce output, it destabilizes the entire chain that depends on that output. Expand the map, and the pattern becomes more complex, not less. Switzerland reports near continuous rain during critical growing months. Fields never dry enough to harvest. Grain sprouts prematurely or decays in place. In England, cloud cover reduces sunlight for extended periods, while intermittent cold snaps cut short already weakened crops. In Central Europe, some regions experience brief recoveries, just enough warmth to trigger growth, followed by sudden reversals. This is not a uniform climate shift, it is oscillation, and oscillation is more destructive than steady change. Crops respond to sequences, not averages. A few days of warmth can trigger growth. A sudden frost after that kills it. Rain saturates soil. A short dry period offers hope, but not enough time for recovery. Then rain returns. Each phase interrupts the previous one. Seeds fail to establish. Plants fail to mature. Mature crops fail at harvest. Loss occurs at every stage. That's why contemporary accounts don't describe a single bad harvest. They describe repeated attempts that never succeed. And when multiple regions experience different types of failure at the same time, the system's natural resilience, its ability to compensate across geography, stops working. Variation, which normally protects the system, becomes part of the problem.
Then there is the sky itself, not as theory, but as recorded observation. People notice sun that appears weak, visible but lacking intensity, light that does not translate into warmth, a persistent haze that doesn't move like normal cloud cover, but sits across the sky for days or weeks. In multiple regions, observers describe unusually vivid red sunsets that last longer than expected. These details align with the presence of volcanic aerosols scattering sunlight, but they also point to something else: prolonged periods where light is filtered and inconsistent. Plant growth depends on more than temperature. It depends on radiation, on the amount and stability of usable sunlight. When light becomes unreliable, even brief warm periods cannot sustain development. Crops receive mixed signals, conditions that trigger growth, but not enough energy to support it. That mismatch leads to partial development, followed by failure. There are also reports of rapid changes in visibility, clear skies replaced by haze within hours, then clearing again. This suggests dynamic atmospheric layers, shifting and redistributing over time. Not a uniform blanket, but a system in motion. And when atmospheric conditions behave dynamically, their effects on the ground become episodic. Not a single event, but repeated disruptions that align with the pattern already seen in agriculture.
As the atmosphere destabilizes growth, the pressure moves into the food chain with mechanical precision. Grain fails first. That immediately affects feed. Hay reserves are finite and calculated for normal variation, not sustained disruption. By mid-season, those reserves are already being used. When they run out, livestock begins to decline. Weight loss, reduced output, then death. And when animals die, the system loses more than food. It loses movement. Fewer working animals mean less plowing, less transport, slower distribution. Goods take longer to move. Loss increases. Supply becomes uneven. Prices spike earlier and faster than expected. Markets react to signals before full outcomes are known. Bread becomes expensive, then scarce, then rationed. Behavior changes. People buy more when they can. Merchants hold stock. Informal trade networks emerge. The formal system loses control over distribution. Substitution begins. Low-quality food, improvised mixtures, anything to extend supply. Nutrition drops. Health follows. Illness increases, not just from disease, but from weakened resistance. Labor efficiency declines, and when labor declines, recovery slows. The system is not just losing output, it is losing the capacity to restore output.
Behavior amplifies the crisis. Hoarding begins early, driven by expectation rather than confirmed shortage. Prices rise sharply.
not in response to measured supply, but in anticipation of failure. That anticipation becomes self-fulfilling. People queue earlier, buy more, bypass official channels. Governments attempt intervention, price controls, relief shipments, but their responses lag behind conditions. Enforcement weakens as survival takes priority. Grain convoys are intercepted, not for profit, but for food. This is not organized crime. It is the erosion of order under pressure. Information becomes uneven. Official reports lag. Local knowledge spreads faster. People move toward perceived supply, often arriving too late or overwhelming already strained regions. Individual decisions, rational in isolation, combine into systemic instability. The cascade accelerates without central coordination. Each action reinforces the next stage of failure.
Then movement begins. Families leave land that can no longer support them. In the United States, farmers move west, not because of opportunity, but because staying is no longer viable. In Europe, populations shift from higher altitude regions into already strained towns. Movement redistributes pressure rather than relieving it. Areas losing population lose labor, delaying recovery. Areas gaining population stretch their resources thinner. This is not adaptation, it is displacement. Contemporary records capture fragments, families gone, communities thinning, new settlements forming under pressure rather than planning. The timeline compresses. Within months, the system moves from environmental disruption to economic stress to social strain to migration. That speed is the signal. It shows how little margin existed in the system before the shock. Primary sources confirm the pattern. Diaries record repeated frosts, failed plantings, constant rain. Parish logs document shortages and shifting conditions. Newspapers note rising prices alongside unstable weather. These accounts do not present a clean narrative. They present fragments, repetition, inconsistency, confusion. People describe what they see, not what they understand. There is no unified explanation in real time. The connection to a distant volcanic eruption comes later. On the ground, there are only symptoms: interrupted growth, unstable conditions, repeated failure. That gap between experience and explanation allows later simplification. A complex sequence becomes a single cause. A chain of failures becomes a summary. And that is where the pressure builds against the standard version. Tambora explains the trigger, it explains atmospheric change, but it does not fully explain the structure of the collapse, the timing, the repetition, the synchronization across regions, the speed of economic and social response. Those require additional layers: regional dynamics, agricultural limits, market behavior, social feedback. The event is not one mechanism. It is multiple interacting systems failing together. When you reduce that to a single line, volcanic ash blocked sunlight, you explain the cause but not the outcome. By the time the sequence completes, the conclusion is precise. 1816 is not just a cold year. It is a stress test. Remove consistency from weather, and the entire structure, production, transport, markets, order, begins to fail in sequence. The system was not robust. It was stable under normal conditions and highly vulnerable under unstable ones. And once that stability was removed, the margin disappeared quickly. That is the detail that does not survive in simplified retellings. So the final question is not whether Tambora caused cooling. It did. The question is what the event revealed when it hit a system with almost no tolerance for repeated disruption. Because if one atmospheric disturbance can expose this much, this fast, then the critical variable was never just the volcano, it was the structure it struck. And if that structure was this close to failure in 1816, then the real problem was already there, waiting. Now, extend the timeline forward, because the effects don't stop when the calendar flips. Early 1817 doesn't reset the system. It reveals what the previous year already damaged. Fields can be replanted, but seed reserves are lower. Livestock losses carry over, reducing traction and transport capacity for the next cycle. Households enter the new season weaker, with fewer reserves and less margin for error. That means even a partial recovery is harder to achieve. Reports from multiple regions show that conditions improve in places, but not evenly and not immediately. Some areas manage a better harvest, but they are now surrounded by regions still recovering from compounded loss.
That imbalance prevents a full rebound. Supply begins to return, but distribution is still uneven. Prices stabilize in some markets, remain high in others. The system doesn't snap back, it drags itself forward, carrying the weight of the previous year's disruption. At the same time, governments begin adjusting policy, not proactively, but reactively based on what they just experienced. There is increased attention to grain reserves, trade controls, and relief mechanisms. But these adjustments are slow and fragmented. There is no coordinated international response, no shared system for stabilizing supply across borders. Each region acts within its own limits. Some attempt to restrict exports to protect internal supply, which only shifts pressure elsewhere. Others rely on imports that are themselves uncertain because producing regions are still unstable. This creates a feedback loop at a larger scale. National responses that make sense locally contribute to imbalance globally. The system, already stressed, becomes more segmented. Instead of buffering shock, it transmits it unevenly. What also becomes visible in this period is how quickly memory begins to compress the event. Within a few years, detailed accounts start to give way to summarized versions. Instead of sequences of repeated failure, the narrative shifts toward a single bad year caused by unusual climate conditions. That shift is subtle but important. It removes the mechanics of the collapse, the repetition, the instability, the cascading effects, and replaces them with a cleaner explanation. That cleaner explanation is easier to teach, easier to remember, and easier to fit into a broader historical timeline that is already crowded with political and industrial changes. But in simplifying the cause, it also simplifies the impact. The event becomes something that happened, rather than something that exposed how the system actually functions under stress. Look at what follows in the decades after. Agricultural practices begin to shift. There is gradual movement toward diversification, toward crops that are more resilient to variability. There is increased attention to storage and transport infrastructure over time. None of this happens instantly, and none of it is framed explicitly as a response to 1816 alone. But the pattern is there. Systems adapt after stress, even if they do not formally acknowledge the trigger. The lesson is absorbed indirectly, not as a single policy, but as a series of adjustments across decades. That's how large systems learn, slowly, unevenly, often without naming the event that forced the change. And this leads to a sharper observation. If the system required years to adjust after a single season of instability, then the margin it had before that event was minimal. It was operating efficiently but not safely. Efficiency reduces redundancy. Redundancy is what absorbs shocks. In 1816, the system shows what happens when efficiency is pushed to its limit. It performs well under expected conditions, but once variability increases beyond a certain threshold, performance drops rapidly. That is not unique to agriculture. It is a general property of tightly optimized systems. They work until they don't, and when they fail across multiple layers at once. So, the continuation of the story is not about the climate returning to normal. It is about a system adjusting to the fact that normal cannot always be assumed. The recovery is partial, uneven, and instructive. It shows where the vulnerabilities were and how difficult they are to correct after they have been exposed. And it leaves one question that is still relevant. If a single season of instability required years of adaptation to recover from, then what does that say about the capacity of any system, past or present, to handle repeated disruptions without breaking in the same way again? Push further into the economic layer, because that's where the longer-term distortion becomes measurable. The shock of 1816-1817 doesn't just raise prices temporarily, it alters expectations. Markets that have experienced sudden scarcity begin pricing in risk more aggressively. Traders adjust behavior, becoming quicker to react to early signs of instability. That changes how volatility propagates. Instead of waiting for confirmed shortages, markets begin moving on signals, weather anomalies, regional reports, transport delays. This creates faster feedback loops. In some ways, it improves responsiveness. In others, it increases sensitivity, making systems more reactive and at times more unstable. The memory of failure doesn't disappear. It becomes embedded in behavior, even when the conditions that caused it are no longer present. There is also a redistribution effect that becomes clearer over time. Regions that managed partial recovery earlier gain relative advantage. They rebuild faster, stabilize sooner, and attract movement. both of people and of capital. Regions that were hit harder or recover more slowly fall behind. This divergence is not always dramatic in a single year, but over a decade it becomes visible. Population shifts, investment patterns, and trade routes adjust accordingly. What began as a climate-driven disruption contributes to longer-term structural changes in how regions relate to each other economically. Again, this is not attributed solely to 1816 and historical narratives, but the timing aligns closely enough to suggest influence.
At the same time, social memory evolves in a different direction. Collective recollection tends to retain the striking elements, the cold summer, the failed crops, but loses the sequence. Stories simplify. The complexity of the cascade fades. That matters because it changes how future events are interpreted. When a system remembers only the headline and not the mechanics, it is more likely to misjudge similar situations later. It recognizes the symptom but not the process. That gap between memory and mechanism is where repeated vulnerability can persist.
Now, consider the informational layer. In the early 19th century, data collection is fragmented. Observations are local, recorded in diaries, parish logs, newspapers. There is no centralized system integrating climate, agriculture, markets, and health into a unified model. That means the understanding of the event is reconstructed after the fact, using pieces that were never designed to fit together perfectly. The volcanic explanation becomes the backbone because it provides a clear, unifying cause. But the local variations, the repeated resets, the uneven impacts, are harder to integrate into that framework. They remain as details, not drivers. Over time, those details become secondary, even though they are critical to understanding how the collapse actually unfolded.
And here is the operational takeaway. When a system lacks integrated visibility, it responds to what it can measure most clearly. In 1816, that becomes temperature and visible atmospheric effects. The deeper interactions, timing mismatches, feedback loops, behavioral amplification, are harder to quantify, so they receive less attention. That doesn't mean they are less important. It means they are less visible in the models that shape explanation. This is not a flaw unique to that period. It is a general limitation of complex systems analysis. What is easiest to measure often dominates what is explained.
So, when you extend the story beyond the immediate crisis, what emerges is not just recovery, but reconfiguration. Economic behavior shifts, regional balance changes, social memory compresses. Explanatory models prioritize certain variables over others, and through all of it, the underlying lesson remains partially obscured, not because it is hidden, but because it is distributed across layers that are rarely examined together.
Which brings the continuation to a precise point. If the long-term effects of 1816 include changes in behavior, structure, and understanding, but the core mechanics of the cascade remain underemphasized, then how confident can we be that the system, once rebuilt, actually addressed the vulnerabilities that caused the failure in the first place?
Now, step back and compare the event to other disruptions, not to merge them, but to identify structure. Across different historical contexts, when systems fail rapidly, the pattern tends to repeat. An external shock interacts with internal constraints, triggering a cascade that moves through production, distribution, markets, and social order. The specific trigger varies: climate, conflict, disease, but the pathway shows similarities. That suggests that what we are seeing in 1816 is not an isolated anomaly, but an instance of a broader dynamic. A system optimized for efficiency, operating with limited slack, encountering a disturbance that introduces variability faster than it can adapt. What makes 1816 distinct is not just the trigger, but the clarity of the sequence. The stages are documented closely enough to trace the progression: environmental disruption, agricultural failure, supply imbalance, market reaction, behavioral shift, social strain, migration, and gradual adjustment. Each stage feeds the next. Each stage reduces the system's ability to absorb further shock. And importantly, the transition between stages is fast. That speed is a defining characteristic. It indicates that the connections between components are tight, with little buffering capacity. When you analyze it this way, the event becomes a model. Not a perfect one, but a useful one. It shows how quickly stability can degrade when variability increases beyond expected bounds. It shows how local decisions aggregate into system-level outcomes.
It shows how explanation can focus on the initial cause while underrepresenting the cascade. And it shows how recovery, even when successful, does not necessarily eliminate the underlying structure that allowed the failure to propagate.
So the logical continuation is not to look for a single hidden factor that explains everything. It is to recognize that multiple factors interacted in a way that exposed a specific type of vulnerability, a vulnerability rooted in timing, coordination, and dependence on stable inputs. Once that is understood, the event stops being a closed historical case and becomes an open analytical reference. And that leads to the final question of this continuation. If the pattern observed in 1816 reflects a general property of tightly connected systems under stress, then the real issue is not whether such an event can happen again under similar conditions. The issue is whether the systems that replace the early 19th century structure have meaningfully increased their tolerance for repeated disruption, or whether they have simply shifted where and how that vulnerability would appear when the next stress test arrives. If you carry the model forward instead of closing it, another layer comes into focus: how information changes the shape of a crisis without necessarily reducing it. By the mid-19th century, observation improves. More weather stations, more systematic records, better communication between regions. On paper, that should increase resilience. Faster information should allow earlier response. But information also accelerates reaction. Signals travel quicker than verification. A report of crop stress in one region moves through markets before full data confirms it. Prices adjust early. Behavior shifts earlier. In some cases, that helps. Supplies are redirected sooner. In others, it amplifies volatility. Markets overreact to incomplete signals. The system becomes more aware, but also more sensitive. That sensitivity is not inherently stabilizing. It depends on how quickly corrective actions can match the speed of reaction. If reaction outpaces correction, instability still grows, just faster and more visibly. Now look at how storage evolves in response. One of the implicit lessons of 1816 is the need for buffer, grain reserves that can absorb short-term disruption. Over time, storage capacity increases in certain regions. Warehouses expand. Trade networks become more organized. But storage introduces its own dynamics. Holding reserves ties up capital. It requires coordination and trust. Decisions about when to release stock, at what price, to which regions. If those decisions are delayed or influenced by competing interests, the buffer doesn't function as intended. It becomes uneven, full in one place, empty in another. And if market participants expect that reserves will be released, they may adjust behavior in ways that depend on that release, creating new dependencies. The buffer exists, but its effectiveness depends on timing and distribution, not just volume. Transport changes as well. Improvements in roads, canals, and eventually railways increase capacity and reduce travel time. That should strengthen the system's ability to balance regional differences. And it does, under stable conditions. But under stress, higher capacity can transmit shocks more quickly. A shortage in one region is felt elsewhere sooner. Price signals propagate faster. Movement increases, but so does the speed at which imbalance spreads. The system becomes more connected. And with connectivity comes both resilience and exposure. The same network that can deliver relief can also distribute panic. Again, the outcome depends on coordination, on whether movement is guided effectively or simply follows pressure gradients created by scarcity and expectation. Behavior adapts too. After experiencing sharp disruptions, both producers and traders adjust strategies. Farmers diversify crops where possible, choosing varieties that hedge against specific risks. Traders monitor conditions more closely, reacting to early indicators. Governments experiment with policy tools, tariffs, export bans, relief programs. Each adaptation addresses part of the problem, but none removes it entirely. Because the core issue is not a single weak point. It is the interaction between multiple components that can all be stressed at once. Diversification helps against one type of failure. It may not help against repeated, multivariable disruption. Policy can stabilize one region while destabilizing another. Market awareness can improve response time while increasing volatility. Each improvement shifts the system's profile, but the fundamental dependence on stable inputs and coordinated timing remains. There is also a shift in how events are categorized. As data improves, anomalies are classified more precisely. Temperature deviations, precipitation patterns, yield statistics. That precision is useful. It allows better modeling and comparison. But it also encourages compartmentalization.
Climate is analyzed separately from markets, markets from social behavior from health. The links between them are acknowledged, but often not modeled in full sequence. As a result, explanations can become more detailed in isolation and less integrated in practice. The initial cause is described with increasing accuracy, while the cascade remains distributed across disciplines. This mirrors what happened with 1816, a clear trigger paired with a complex outcome that is harder to capture in a single framework.
So, when you extend the logic further, the question shifts again. It's no longer just about whether systems have improved since 1816. In many ways, they have. Better information, larger reserves, faster transport. The question is whether those improvements have increased tolerance for repeated, multivariable disruption, or whether they have changed the speed and visibility of failure without fundamentally altering its structure. Because if the core dynamic, tight coupling, limited slack, dependence on timing, remains, then the system is still vulnerable. Not in the same way, not in the same places, but along the same pathways. And if that's true, then the most important part of 1816 is not the specific conditions that caused it. It's the sequence it revealed, and how easily that sequence can reappear when variability exceeds what the system is built to handle.
Take the sequence one step further and look at how thresholds behave, because that's where the pattern becomes measurable instead of descriptive. Systems don't fail gradually. They operate within a range and then cross a boundary where behavior changes abruptly. In 1816, that boundary appears when variability exceeds what planting schedules can absorb. A single frost doesn't break the system. A second one, after replanting, begins to. A third, combined with saturation or low radiation, pushes it past recovery. That's a threshold defined not by magnitude alone, but by repetition within a limited window. Once crossed, the rest of the cascade becomes much more likely. Feed reserves begin to draw down early. Animal strength declines sooner. Market expectations shift before harvest data is complete. Each of those transitions represents a threshold event, small in isolation, decisive in sequence. What matters is not just how extreme a single input is, but how many times the system is forced to restart under constrained time and resource conditions. That's the difference between stress and failure.
Now, consider how these thresholds interact. Agricultural thresholds trigger logistical thresholds. When feed drops below a certain level, transport capacity doesn't degrade smoothly. It drops in steps as working animals become unavailable. That creates discontinuities in distribution. Routes that function one week fail the next. Those discontinuities feed directly into market thresholds. Once supply becomes unreliable rather than simply reduced, pricing behavior changes regime. Participants stop treating scarcity as temporary and begin acting as if it could persist. That shifts incentives. Holding stock becomes more attractive, early purchasing becomes rational, and volatility increases. These are phase changes, not linear adjustments. And because they are linked, crossing one threshold increases the probability of crossing the next. By the time social thresholds are reached, cues turning into conflict, enforcement losing effectiveness, the system has already transitioned through multiple earlier states. The visible disruption is the end of a chain that began quietly with timing mismatches in fields.
Feedback loops determine whether the system can recover once those thresholds are crossed. Negative feedback stabilizes. Loss in one area triggers compensating action elsewhere. Positive feedback amplifies. Loss triggers behavior that increases loss. In 1816, positive feedback dominates at key points. Early price increases encourage withholding, which tightens supply further. Movement toward perceived surplus regions overloads those regions, reducing their capacity to help. Labor loss slows recovery, which prolongs scarcity. These loops don't require coordination. They emerge from local decisions interacting under shared constraints. The absence of strong negative feedback, robust reserves, rapid coordinated redistribution, reliable information, means there is little to counteract amplification once it begins. Recovery then depends on external relief from the initial stressor, improved weather, rather than internal system correction. That's why the system drags forward instead of snapping back.
Information timing sits at the center of these dynamics. Early signals drive early action, but signals are noisy. In a fragmented information environment, reports of failure and reports of recovery coexist without clear weighting. Actors choose based on proximity and trust, not on complete data. That creates asynchronous reactions. Some areas behave as if the crisis is deepening, others as if it is easing.
As these behaviors interact through trade and movement, they generate additional volatility. Faster communication can reduce lag, but it can also synchronize reactions, causing broader swings if many actors respond to the same signal at once. The key variable is not speed alone, but alignment between signal, interpretation, and corrective capacity. If corrective actions, moving grain, releasing reserves, coordinating policy, cannot keep pace with reaction, then better information accelerates instability instead of dampening it.
Finally, consider path dependence. The order in which events occur shapes outcomes as much as their magnitude. If a brief, stable period had preceded the worst conditions in 1816, reserves might have been higher and thresholds harder to cross. If transport had failed before markets reacted, price spikes might have been delayed, but shortages more severe locally. The actual sequence, early planting attempts, repeated interruptions, early reserve drawdown, rapid price response, locked the system onto a particular path where each step constrained the next. Once on that path, options narrowed. Replanting consumed seed that could not be replaced. Animal losses reduced capacity that could not be quickly rebuilt. Market expectations hardened in a way that influenced behavior even as conditions fluctuated. That is the structural lesson. In tightly coupled systems, sequence governs outcome. And when sequence pushes the system past multiple thresholds in quick succession, recovery becomes contingent not